Good morning, everybody. I'm Kaca, for those that don't know me, and I'm a second-year graduate student working with Brad, so inevitably working on an anoxic event. And today I'm going to be focusing on improving the aptine chronostratigraphy to support studies of oceanic anoxic event 1A. So why is there this need to reevaluate the aptine timescale? So currently in the literature, there are two conflicting timescales. One that's placing the onset of the aptine at roughly 120 million years ago, and the second 5 million years after that. OAE 1A is constrained to roughly 120 million years ago. So this is problematic. So because depending on which time scale you're referencing to, the oceanic or OAE 1A doesn't even occur in the aptine. So this brought this need to refocus some attention on the aptine timescale. And the most recent version of geologic timescale places the onset at 121 million years ago. So there's still a lot of uncertainty with the aptine timescale, especially in respect to the timing of events leading up to and after the anoxic event. So this is where one way to improve this is using an astrochronology. I'm so sorry, a little nervous. And so that's essentially converting stratigraphic depth to time. And in order to do this well, there are two things that you need. First, you need record of sedimentation that is driven by external forcings or Milankovitch cycles. So to put this into context, here's a geographic map of the aptine showing the two sections that I'm working on in yellow. So first is the Vicentin Basin, which is in modern-day France. And so here's the core that I'm looking at. And this summer, I did some XRF analysis. And so here are some preliminary data shown here in green. And so hopefully it's pretty obvious to see that this calcium data set shows some rhythmicity. And this suggests that there is external forcing present in this core, which is helpful because from that, we can create a quote unquote floating time scale, which essentially means that we can understand how much time is passing due to our understanding of the Milankovitch periodicities. So something like 100 kiloyears versus 400 kiloyears. The second component to this is anchoring this floating time scale using high precision ages. And so this comes from the second section over here in Hokkaido, Japan. And so this section contains rocks of similar age that contain rhyolitic tuffs. And so that's really important because we can determine age constraints. So collaborators at UW-Madison are working on that right now. They have about 13 different tuffs that they're going to be using uranium lead analysis on. And so then these two sections will ultimately be correlated via carbon isotope stratigraphy. And so with this floating time scale coupled with this these anchored tie points, we'll have the most high resolution aptine time scale. So it sounds great. Next slide. And so to tie this back into OAE 1A, this is a super busy diagram. I'm not going to go through it, but this is highlighting all of the key studies that talk about OAE 1A dating back to the late 90s over here on the far left. And so we could go through this, but I will just highlight that there are different definitions in terms of the onset, the duration of the event, and there's especially a lot of discrepancies within the biostratigraphy of OAE 1A. So hopefully with this redefinition of the aptine timescale, we can kind of get a better idea of different timing events that pertain to OAE 1A. So thank you for listening, and I'll take any questions if there are any.